Okay, I think I'll start now. All right, so just confirm, you can see my screen, right?
Can, Doctor.
All right, okay, right. Okay, so far, we've tackled sectional design for fracture, okay? So far what we've done is this, okay? Yeah, yeah, so just to recall what we've done so far, we've done a beam, and I taught you how to design and check how much reinforcement, yeah? How much reinforcement? I taught you how to calculate AS, yeah? AS being the area of steel required, okay, for the reinforcement, okay? Once you know area of steel required for reinforcement, AS, then you can decide how many reinforcement bars to put in, okay? There's a table somewhere out there to teach you how to decide how many bars to put in, okay? But we don't really have to go through that, okay? That's basically what we've done so far, okay? Now, obviously, this is in this case lah, okay? So if we look at it from sideways, basically, I taught you how to calculate how much reinforcement you need at the bottom of the beam, okay? This is what we've done so far. Now, there are cases, as I mentioned earlier, there are cases where, okay, so far we've done only reinforcement at the tension zone in the bottom. Okay. Now, there are instances where you actually need reinforcement at the top as well. I mentioned that earlier. Okay. So there are instances where situation. So there are situations or instances or cases where reinforcement, okay, where reinforcement is required at the top of the beam. Okay, so now we are going to look at several cases where reinforcements required at the top of the beam and how you design for those. Okay, now generally I can think of two. The first case is when this is quite straightforward, when beam is continuous, therefore tension zones can develop at the top of the beam. Okay, so this is one situation. So this is one example where you can get reinforcement at the top of the beams. Okay, so example is I've gone through this with you, but I'm going to go through it quickly again. So continuous beam, something like this. Okay, and your bending moment diagram may look something like this. Okay. Okay. So what you get is, for I'm gonna break this up into segments. Okay. I'm gonna break this up into segments. Yeah. Okay. So I've basically broken up the beam into segments. Okay. Now, segment 1 is actually, let me draw it closely. Okay, segment 1 is there. Segment 2 is there. Segment 3 is there. So 3, and segment 4 is there, and then segment 5 is there. Okay, 5 segments. Okay, now pay attention to how I broke the beam into segments. Okay, I break the beam into segments where the bending moment becomes 0. Have you noticed? At that point, it's 0. Yeah, because it goes in the tension zone and changes to compression. It goes from sagging. This is sagging. When the bending moment diagram goes above the beam, it's called hogging. Yeah, I don't know whether you've learned this term before. When the bending moment diagram is below the beam, it's called sagging. When the bending moment diagram is above the beam or over the beam, it's called hogging moment. Okay, so you notice when the curve goes from sagging to hogging, that's where I break the beam into a segment. Okay, and then where it goes from hogging to sagging again, I put another segment. So the reason why I do that is obviously this, where it goes from sagging to hogging, is where the moment, this is the point where the bending moment diagram goes from bottom of beam to top, and vice versa, and vice versa, and vice versa. Okay, so your tension zone also changes. Okay, in the sagging zone, the tension zone is at the top, is at the bottom. Yeah, now when it goes into hogging, the tension zone goes to the top. Okay, so the tension zone is basically the place where the bending moment diagram occurs. Okay, I think I mentioned that earlier. Okay, tension zone is basically where you draw your bending moment diagram. So you can see over the support, the bending moment diagram is actually drawn on top of the beam. So when you reinforce your beam, you always have to reinforce the tension zone. So this is your beam, okay? Oversized, but doesn't matter. I just need to illustrate my point. So when you reinforce your beam, segment 1, you do it normally. Yeah, because the tension zone is at the bottom. So you design the reinforcement at the bottom. Now, zone 2, segment, segment 2, the bending moment diagram is now at the top of the beam. That means the tension zone is also at the top. So you need to put reinforcement at the top, because that's where the tension is. You only need to put reinforcement where the tension is. Okay. Now, segment 3 is at the bottom, so you need to put reinforcement at the bottom again. Segment 4, bending moment is at the top, and then finally 5 at the bottom again. This is how you reinforce the beam. Now, obviously, you cannot just stop. You cannot just stop right there. Normally, we extend it in a little bit. We extend it a little bit. We extend it in a little bit as well. Okay. But generally, that's the principle. Okay. So, because of this, you need to put reinforcement at the top. So, how do you design? How do you do the design? Okay. So, for segment 1, if we do a cross section here, the beam looks like this. Yeah, the beam looks like this. So, a beam that looks like this, do you know how to design? I taught you how to design Suragan. Yeah, last week. Yeah, a beam like this, neutral axis somewhere here. You know how to design, right? I taught you last week. If I give you the beam size, I ask you to calculate how much reinforcement you know how to do that, right? Yes or no? This is what we done last week. Yes or no?
Yes.
Okay. Now, okay, so segment 1, yeah, is this. Now, segment 2, how do you think we design the beam? Segment 2, the tension zone is at the top, so reinforcement has to go in the top. How do you think we design the beam? The neutral axis will be somewhere, yeah. Hey, why is it deleting? Okay, neutral axis somewhere there. How do you think we design this beam? What is the difference between 1 and 2? What what is the difference between 1 and 2? Are you taking notes? Are you taking notes for this?
Yes.
Yeah. What's the difference between 1 and 2? Okay, you take your notes, you take your notepad, you turn it upside down. You take your notepad now, you turn it upside down. Does segment 1 become segment 2? You ignore segment 1. Or rather, you look at segment 1. If you turn segment 1 upside down, does it become segment 2?
Yes.
Yeah. So what does that mean? That means you design the beam upside down. Lah. You just design the beam upside down. Okay? So how do you design segment 2? The way you design segment 2 is you turn segment 2 upside down temporarily. Turn upside down temporarily. You turn it upside down temporarily. If you imagine it's the normal orientation, you design it. After you finish design, you know how much reinforcement you need, you turn it back. Then it's the same reinforcement you need here. You just turn the beam upside down. Okay? That's how you do it. So that's how you do design. Okay? Now, for this, I'm not going to teach you in detail because this will be an assignment. Okay? So for reinforcement, so for reinforced concrete design, there will be an assignment where you have to design a building or maybe a frame, entire frame. Okay. So for that frame, you need to know how to do continuous beam design. You need to know how to do the analysis as well. Okay. So for the design part, that's how you do. Okay. For the segment where the moment is sagging, you design it as normal. For the segment where it's hogging, you turn the beam upside down. That's how you design it. Okay. Now, this is the easy part. The difficult part is analysis. The difficult part is the analysis part. How you actually get the bending moment diagram. Okay. Now, as I told you, continuous beam. Bending moment diagram looks something like this. How do you know the values here and here? To do design, you need to know the values. Okay? Maximum moment values. How do you get the values? How? Anyone? Quick. Jangan malu-malu. If you know the answer, just let me know.
Is it by finding the maximum bending moment?
Yeah, correct. But how? How do you find the maximum bending moment?
At the top, WL square over 24, I guess, or 8.
Okay. So if it's simply supported, then yes. The moment at the center is WL squared over 8, correct. But continuous, it's not that straightforward. Okay. I don't need the formula. I need to know the method. What method are you going to use? Actually, I think you have learned this before. The method.
BMD.
Yeah, BMD is bending moment diagram. What method are you going to use? What? Okay, BMD. Yeah, BMD is this. This is BMD, bending moment diagram. But what method are you going to use to draw the bending moment diagram? To draw the bending moment diagram, you need to know the moments, the maximum bending moment at each point. How do you do it? There's a method. I think you learned it. You learned the method during Theory of Structure 2, TOS 2. You try to recall TOS 2. There's a stiffness here. TOS 2. Okay, TOS 2. Do you remember drawing a table? Do you remember? Okay, TOS 2. Do you remember a lecturer giving you something like this? Yeah. And then they give you the load, or maybe 10 kilonewton per meter run. Ask you to draw the bending moment diagram. What method are you going to use? Do you remember? And then maybe stiffness, maybe the stiffness as well. This one is, I don't know, maybe 1 EI. This one maybe 3/4 EI. This one maybe 3/4 EI. Then you need to draw a table. You need to draw a table. So let's say this is support A, support B, support C, support D. You need to draw a table A, B, B, C, and then C, D. And then you need to know the stiffness. So the stiffness here, I don't know. You have to calculate the stiffness, and then you have to calculate distribution factors dF. And then you have the load maybe. And then you have the FEM, the moment that you start with. And then you have calculate balance. And then you calculate carry over moment. Oh, yeah. Have we done this before? Does it look familiar?
No, doctor.
No? Huh? Have you so wait, when you said no, I turtlean my sweet. I actually I've got sweet in my mouth when I was teaching. When you say no, I swallowed my sweet by accident. I need to drink water now. Wait. That's how shocked I was. Cannot recall this method. TOS 2. Okay, the name is.
Doctor, we're still taking TOS 2.
Oh, you're still using TOS 2. Oh.
Yes, doctor.
Oh, TOS 2 at the same time as RCD, yeah? Okay. Who's teaching?
Dr. Fauzi.
Okay. Can you request him, ask nicely, ask him to teach you this method quickly? Moment distribution. Has he done this with you? Moment distribution? Not yet. Yeah, not yet. Have you haven't covered this yet?
No.
Oh, okay. Can you ask him nicely to maybe do this earlier, kalau boleh? Because you need this method. You need to know this method to solve your continuous beam. And this continuous beam will be given to you as an assignment. Yeah. I will start passing out assignments next week. So you need to know this method to do the assignment. Okay. I can go through it with you, but it's gonna take a very long time. That's a problem. All right. So yeah. Next class, ask Dr. Fauzi whether he can do this with you earlier. Moment distribution method. Okay. It's something like this. You're gonna start drawing a table basically. You need to start adding. Basically, it's not difficult. In this table, you're gonna do addition, subtraction, multiplication, and division. Okay, and then you're gonna get the final answer. Basically, from this using this method, you will be able to get the moments. You will get the moments, the maximum moments in the beam. You will get the maximum moment here. You can get a 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 moment here. Okay, using this method. All right. So, okay. Now there are actually two methods. Yeah. So let me just analysis of continuous beams. There are actually two methods. One is moment distribution method. Which Dr. Fauzi will teach you. Okay. Moment distribution method. Dr. Fauzi will teach you this. Now, there's another method, a simplified method. There's a simplified method, but the simplified method comes with a lot of rules. Okay, I'm going to talk about a simplified method now, but it comes with a lot of rules. The first rule is the span, the span of the beam, yeah, the length of the beam cannot differ by more than 15%. So meaning the shorter span versus the longer span, the difference cannot be more than 15%. The difference between the shorter span in the beam and the longer span in the beam cannot be more than 15%. Okay? That's one condition. The second condition is the variable action has to be less than, so the variable action, again, it's live load. Variable action means live load. The variable action has to be less than the permanent action. Permanent action is dead load. Okay. So if your continuous beam satisfy this condition, then okay, you can use this simplified method. Okay. So for the simplified method, okay, to get the bending moment diagram, you have to follow this. Okay. There's end span and interior span. Okay. You can use this simplified formula. Why can't I delete? Okay. Okay. So for bending moments, they are coefficients. They are basically coefficients that you can use. Okay. So end span, you always start from 0. Okay, and then you have your downward moment. Sorry, let me draw this in red. Draw this in red. Okay, the bending moment. So let me draw the bending moment diagram in red. Okay. Okay. Now, here it's 0.09 FL, the coefficient. At the support, it's 0.11 FL. Okay. At the interior span, you can use this. Okay. At the supports, 0.10 FL, 0.10 FL. And in the middle, 0.07 FL. Okay. Shear. Now, after we finish flexure, I will teach you how to design for shear. Okay. For now, we are not going to worry too much about shear forces yet, but you need to know how to calculate it. Okay, because we will soon learn how to design for shear as well. Okay, shear failure. Okay, so for shear forces, you will use these coefficients 0.45 F and 0.60 F. Yeah. And this is for the end span. For the interior span, you do this, where this is 0.55 F, and here is also 0.55 F. Why did I use white for this? It's supposed to be using red. 0.45 F, 0.60 F. Okay, so these are the coefficients you use for the simplified method. But simplified method, there are rules that you need to follow. Okay, the rules at the top. Okay, I will go through this with you. The simplified method I will go through with you because I don't think Dr. Fauzi will cover this. Okay, he will only cover the moment distribution method. Okay, so this one I'll go through an example with you. All right. So there are a few more things that you need to know. Okay, from here, F. What is F? You're gonna ask me. Apa to F? Because in the coefficients you have F and L. All right. So what is F? So F is the total ultimate load on that span, which is the formula is 1.35 GK plus 1.5 QK. So you still remember what GK and QK is? What's GK and what's QK?
Dead load and live load.
Yeah, correct. It's here. Okay, thank you. Variable action, live load is QK. Permanent action, dead load is GK. Okay. Okay, good. Thank you. L is the span, or rather the effective, or rather the effective span. Okay. Okay. You copy this down quickly. We'll go through a quick example. All right.
Sorry, doctor.
Yes.
For the bending moment, you mentioned end span and interior span.
Yes.
The percentage for like 0.1 and 0.09, are these fixed values or you just assume?
Yes. So these are coefficients that you can use for the maximum bending moment at the end span, bottom and top. It's so those values 0.09 FL, that is the bending moment at the bottom, the maximum bending moment at the bottom. 0.11 FL is the maximum bending moment at the top. Is that your question?
Yes. Okay, doctor. Thank you.
Okay. So in the interior span, 0.10 FL is the moment at the supports at the top, and 0.07 FL is the moment in the middle at the bottom there. Okay, I'm supposed to put across, that makes it clear. Okay, thank you. Thanks for bringing this up. Yeah. Okay, so let's do a quick example to see how we calculate this. Is there example here in the book? This is redistribution, so this one's different. Nah, let me do my own example. Okay, let me do my own quick example for this. All right, okay. Example. All right, so I have a continuous beam. Yep. The spans are sorry. The spans are, we make this 8. We make this 8. And, wait, let me get my calculator. This one is 7.5. Okay. So this is support A, support B, support D, support, sorry, C and D. Okay. Okay, and then UDL along the beam. Okay, so the UDL along the beam, GK, the permanent action. Gonna make it, what's a normal slab? 0.15, sorry, 0.15 times 25 times maybe 6. Okay, let's say 20. Yeah, kilonewton per meter. Right? QK, let's say 18. Okay, QK is 18. 18. Okay. Okay. All right. Okay, so sketch the bending moment diagram and shear force diagram. Okay, for the continuous beam. Above. Okay. So there are two ways. You can do this. Okay. You have so two methods. You can either use moment distribution method. So the moment distribution method is a longer method. It takes more time. Okay. But it will give you the same answer. Okay. And for this one, you can either refer to the book that I shared with you, the Reinforced Concrete Design book. There's actually an example in there on page. There's actually an example in there. on page 34. Okay, there. So you can learn this from TOS2 when Dr. Fauzi teaches you, or you can learn it from the book, the Reinforced Concrete Design book that I shared with you, the PDF file. Yeah. There's an example on page 34. Okay, for this method. Okay. Now, there is also a simplified method that you can use. I will teach you the simplified method today. Okay. So today we are going to use a simplified method. Okay. Using the simplified formulas, the coefficients. Okay. Now, before you can use simplified method, you have to do two checks. Okay. To be able to use a simplified method, you have to check these two things. You have to check these two things. Okay. You have to check these two things. If your continuous beam doesn't meet these requirements, you cannot use this method. You have to use moment distribution method. Okay. Simplified method can only be used if you meet these two requirements. Okay. Let's do a quick check. The first one is the difference between the spans cannot be more than 15%. Okay. The difference between the span lengths cannot be more than 15%. So is it more than 15%? Is it more than 15%? What's the shortest one? Shortest one is how much? Let's do a quick check. The shortest span is 7.5. The longest span is 8 meters. Is this more or less than 15% difference? How much percent is this? How much percentage is the difference? Okay, the difference is in length is how much? 0.5, right? Agree?
Yes.
Yeah. How many percent is that? Between the difference between the shortest and the longest, it's half a meter. Is that less than or more than 15%? Do you think?
Less than 50%.
Yeah, correct. Okay. How much percent? How many percent is this? 0.5. Let's divide it by 8 lah. Or 7.5 times 100. Wow, it's about 6. It's about this much, 6.7%. Less than 15. So, okay. So, first requirement. Okay. Now, there's a second requirement. What's the second requirement? What's the second requirement? Quick. What's the second requirement? The second requirement is easy. What is it? What QK cannot be more than GK, right? Quick, someone. The quicker you answer me, the quicker we can end the class. Otherwise, I'm gonna just keep going until I finish what I want to finish. It may be more. It may we may go into 1:15, 1:30. So the more you help me out, the faster we can finish the class. What's the second requirement? What's the second check that we have to do? Quick. I also want to go for my lunch. Quick. Maybe a lady this time. Quick. Safawati, are you there? Can you help me? Zachary, are you there? Oh, Samantha dah kah? What happened?
Hello, doctor. Sorry, but for my case, because I'm capturing so that I can understand your lecture, so I didn't take notes. So for me, the only thing that if you can just go up and
Okay. No, okay. It's okay. I want someone else to answer.
Life load must be smaller than dead load.
Yeah, correct. Okay. QK has to be less than GK. In this case, is that the case? How much is QK? How much is QK?
1.35.
What's the QK here? There.
18.
Yeah, 18. What's GK? 20. So yes, 18 is less than 20. So second requirement, okay. Okay, so we meet the first requirement, we meet the second requirement, fine. We can use the simplified method, okay? Okay, so we can use the simplified method. So simplified method for BMD, you draw the frame, or rather you draw the continuous beam. Okay, you draw the continuous beam. Okay, the bending moment diagram looks something. It's gonna look something like this. We don't know the values yet. Okay, but we know here it's 0. What is it? 0.09 and 0.11. Okay, so we know here is 0.09 FL. Here is 0.11 FL. Here is 0.11 FL. Here is 0.07 FL. Then, so this is end span. Okay. This is also end span. The middle is interior. Okay. So therefore, this is 0.09 FL as well. And then here is 0. At the ends, on the left hand end and on the right hand end, it's 0 and 0. Okay. So to get the moment, we have to calculate F and L for each span. So for this span, what is F? For the first span, well, L is 8. L is 8. F is 1.35. Now, it's the the load that I've given you, the QK, it's UDL. Okay, it's UDL. So you have to turn it into F, a force. So it's 1.35, 20 plus 18. You have to multiply it by the length once to turn it into a force. Okay, so here 1.35, 20 plus 18 times 7.5 because the length is 7.5. So here again, here is the same as this. Okay. So now you know your F, you know your L, you can calculate your moments. Okay. So SFD, you do the same thing. Okay. SFD, you do the same thing. Follow the similar methods. Okay, you give me the answer. We will continue with this tomorrow morning. Okay. So tomorrow I will ask you to give me the answer for this tomorrow morning. Okay. Okay. Now I'm going to share the attendance screen. Make sure you scan and do the attendance now. Okay.